We're excited to launch into session number 2 here at day 4 of Expand North Star. This particular conversation, again, is in keeping with the focus on unicorns this morning. We're investing in the quantum world of tomorrow, a pipeline or a pipe dream. That's the intriguing title for this session. I'm very pleased to welcome back on stage to moderate this session a familiar face here at GITEX Global and at Expand North Star. We've had him with us for the last few days. I got a chance to get to know him yesterday, so I'm pleased to say he's a very approachable and intellectual gentleman. Mike Butcher, editor-at-large at TechCrunch UK. He's going to be comparing this next fireside. And with him, our special guest, Christian Weedbrook, who's the CEO and founder of Xanadu Quantum Technologies, all the way from Canada. Please do give them both a big round of applause. Thank you. Welcome, Christian. Over to you, Mike.
Thank you so much. Hi, everybody. How are you? Well, come on in, everybody. We're going to have a fantastic conversation about quantum computing. Super excited for this. Mike Butcher from TechCrunch, and it's a delight to be here back at GITEX and Expand North Star once again. We're going to be talking about quantum computing, the quantum world of tomorrow. Will it arrive? I think that one of the Christian Weedbrook from Xanadu Quantum Technologies, one of the things about quantum computing that people often say is that it's just around the corner. It's coming soon. It'll happen next year. It reminds me a little bit of the old story about mobile technology, and of course it took 20 years for that to happen, and then eventually, of course, nobody talks about when's mobile happening, ha ha ha. So when is quantum computing really going to arrive on our doorstep?
Yeah, thanks, Mike. So the first thing is, if you expand out enough time, it will happen. There's some people that say no matter how long you wait, it'll never happen. Us at Xanadu and a lot of people now are convinced it will happen. So like you said, it's a question of when. The first thing perhaps to know, if the audience doesn't know, is quantum computers do exist now. They're just not capable of solving important business problems yet. So really small-scale quantum computers. And we believe over the next 3 to 5 years, they'll be able to start solving really important business problems. The big milestone that was achieved by Xanadu and also by Google last year was quantum supremacy. So that was a point where you would have choose a well-defined math problem. It's not a business problem, but it's an important stepping stone. And then you go head-to-head with this math problem that you believe to be hard. And what we did is we benchmarked it on the world's fastest supercomputer in Japan. It would have taken, if you used all 7 million cores, 7 million years to solve this problem.
On the world's fastest supercomputer?
Yes, exactly, using all their cores.
7 million years to solve the problem.
That's right.
Right.
And so our computer, which we called Borealis, based in Toronto, it took 2 minutes to solve the same problem.
Amazing.
And so that gives you a flavor, a feel of what's going to happen with quantum computing. But as mentioned, this was for a very esoteric math problem, but it's an important stepping stone, particularly for those who thought that you couldn't even achieve it for a math problem. So the next stage now is to work on applications. But to your point, you do need to build up the quantum computer. We had 216 qubits for that computer. You now need to get to 1 million to start solving important business problems.
These qubits are really the key point about quantum computing, aren't they?
That's right. So a qubit is a quantum bit. It's what it stands for. And essentially, it's like in classical compute or normal compute, you have bits of information that are used as the input, used to process, and used to read out. And we have quantum versions of all those 3 different layers. Qubit count is important, but there are many other aspects of it as well. So as you scale up, you need to make sure you have coherence. So essentially that means as you scale up, you need to have all the important quantum properties like entanglement, superposition, low error rates. Those properties still exist as you scale up to millions, which is very hard to do. And that's for the next few years what everyone's after.
Let's hear a little bit more about Xanadu. Fantastic name, by the way. What in your view sets you, Xanadu, apart from other companies looking at quantum computing, building quantum computers. What's your special sauce?
There's a few things that kind of all add up together. So the first thing is we're full stack, which is not unusual. There's others that do that. Essentially, full stack means you do hardware, software, applications, and then you wrap that all around with a cloud platform. So we have Xanadu Cloud and all those different layers. That's one thing. Not everyone does that. And the other key differentiator is the fact that we're using light or photons to build our quantum computer. So that's also very unique. You can think of things in nature being composed of either electrons or photons. We're very familiar with things built out of electrons, electronics. And there's quantum companies building things out of the quantum version of electronics. That would be superconducting qubits and ion traps. For us, we're going the other direction using light or photons.
Right. Say that again. LiDAR photons.
Light or photons.
Light.
You're making fun of my Australian accent now?
Sorry. Absolutely. Now, one of the big questions is about quantum is that it's fiendishly hard on the hardware side of things. People are talking about, you know, the amount of cooling that a quantum computer needs. Some people have tried to build quantum computers that will operate at room temperature. What's been your solution?
Yeah, I would say, you know, nearly all actually have some form of cooling, including Xanadu.
Yeah.
But most of them actually have the whole computer in a cryostat or cooled down. For us, getting to 1 million qubits, just to give you an idea, it would actually be about an acre of land, so half a football field. So what that means is it'll be a small data center with hundreds or thousands of server racks. Each server rack will have a small amount of qubits in it, but then you network them together using light or photons to build a even more powerful quantum computer of 1 million qubits. Now, in terms of that small data center, Xanadu's cooling footprint will have about 10% at very cold temperatures, but 90% is actually at room temperature.
Right.
And why that's important is because you want to iterate as fast as possible. So you want to have the chips outside the cryostats, which we do, and you also want to be able to, you know, ultimately not have to put FP. There's a lot of classical compute that goes into building a quantum computer. So other approaches will have to work out how do you put electronics, how do you put FPGAs actually into cryostats that operate at 1/1000th of a Kelvin, 0 degrees Kelvin. So that's really important too. We don't have to worry about that sort of stuff.
Right, I see. So that's, and you're operating in Toronto, is that right?
Toronto, that's
right. Toronto. Now, one of the things you're looking at is electric batteries, electric vehicle batteries, I know. Now, obviously, the transition to net zero is very much higher on the policy agenda for governments, and you know, our transition to electric vehicle technology is very obviously motivated by carbon emissions, but also pollution. But of course, one of the sticklers and one of the problems that we're encountering, of course, is battery life and range of electric vehicles that still isn't quite up there against the internal combustion engine. If we can make electric batteries more efficient, last longer, give us better range, then that's going to solve a whole lot of problems. But I know that you're working on technology what is it to do with efficiency, or just explain to everyone what you're doing.
Yeah, in terms of batteries, the idea there is once you have a powerful enough quantum computer, so 1 million qubits, what would you do with it? And Xanadu and a lot of the people in the industry believe quantum chemistry is the earliest low-hanging fruit for a quantum computer of that size. And so we've chosen more specifically material design and simulations, and even more specifically next-generation batteries. So as you mentioned, these are the things that we're looking at. So if you had a quantum computer, how could you actually develop new materials that would make a battery for next-generation battery for electric vehicles safer, longer range, higher capacity, and all that sort of stuff. And the idea there is new materials are perhaps needed. And the overall really exciting part is all of this is quantum mechanical. Quantum chemistry is inherently quantum mechanical. So it's better off, instead of using classical computers, even if they're supercomputers, it's still only an approximation to the results that you want. So another way of looking at that is when you're searching for materials, you're not searching the whole space of options. And so the idea is a quantum computer will be the best type of device that can give you a better and more accurate description of what's happening on the atomic level.
Right, I see. And I mean, how close do you think, to solving that problem?
Yeah, so that's a two-pronged approach, is really understanding, well, the interesting thing is, let's assume we had 1 million qubits today, a really powerful quantum computer that could solve these things. It's not like a new computer chip, like an Intel or NVIDIA, where you can take the chip out, an old one, and put a new one in. It's like, well, what I was doing before and is now running faster. You don't actually know how a quantum computer is going to work because it's so fundamentally different. Yeah. So we know it's going to be able to do quantum simulations and so forth, but it's not like taking out a chip and putting in a new one and it runs faster. So we have to work with automobile companies. The good thing is they have small quantum teams, all the large ones do. We work with all of them, and we have to understand and ask some questions. Well, where is the computational bottleneck in your calculations? And then we have to search and understand the mathematics at a fundamental layer, why it's slow, and map those mathematics to quantum physics mathematics. So the reason I bring that up is there's still work to be done as we wait for 1 million qubits. So that's a challenge. And the other challenge is obviously getting to 1 million qubit quantum computer, which is very difficult, as I mentioned before.
Yeah. Now, one of the subjects that often comes up around quantum computing is the potential for it to break encryption and military-grade 256-bit encryption, that it could potentially, a quantum computer, some people theorize that it could break the encryption around blockchains, Bitcoin, Ethereum, etc., which is obviously quite a big math problem, to put it mildly. What's your estimation about whether or not that would be possible?
So the theory does say, in fact, that would be possible to do. The question is when that could happen. We were just talking about 1 million qubits as being the lowest hanging fruit to solve important, early problems in quantum chemistry. Those sorts of problems in terms of hacking the internet, breaking RSA, elliptic curve, and things which blockchain and that are reliant on in terms of certain aspects of authentication. The current thinking is you need tens of millions of qubits, physical qubits, to solve problems like that. So unless there's a huge breakthrough, that is most likely to happen in the 2030s, so next decade. But the good thing is there's a solution for that, and the solution is to replace the mathematical codes of RSA and elliptic curve with different types of math. And so companies are working on that. It's called post-quantum cryptography. Right. And you can actually find mathematics that a quantum computer kind of looks at and says, look, we don't know how to do anything with that. Right.
Oh, interesting. That gives us some hope that all of our bank accounts won't be immediately broken in about 5 years' time. Lastly, obviously, one of the big themes of GITEX this year and also this stage is the rise of generative AI. And, you know, I'm sure you and I have been around long enough to, people have been talking about artificial intelligence for many years, but in the last year, the rise of generative AI does seem to be a real step change in the whole area. What's the relationship, in your view, between this next new world of quantum computing that's gradually starting to appear, and generative AI? Would it be, for instance, are we bordering on the point where we might sort of get artificial general intelligence being able to run via generative AI on a quantum computer?
So the quick answer is it's unclear how quantum computing can help AI. Having said that, Xanadu was the first, had the first 2 research papers on what we call quantum GANs, generative AI. And we have one of the best teams in quantum AI that has been working the last few years on this very problem to understand how. The current thinking, and this is not proven yet, but it's very exciting, is when you look at ChatGPT, I think it's up to trillions of parameters that need to be trained, hundreds of millions of dollars for the cloud compute. That's not scaling well. It's already very difficult, but it doesn't seem like it's slowing down. So the trend is upwards. So a lot more money, a lot more parameters. The hope is maybe you could have a quantum computer that can use a simpler model for a quantum computer. So now you can do the same thing and can keep this upward trend, but using a quantum computer. So it's easier to train, it's easier to do inference. Again, it's still speculative, but that's the idea where a quantum computer may help.
Right. Certainly, I mean, we heard earlier from Jonathan Ross from Grok about his work on TPUs, which are sort of the next, some people are talking about the next stage on from things like GPUs, and how much faster these AIs these large language learning models can run on these kinds of chips. And so thinking about how fast quantum computing could be, the sort of the Shangri-La, the Xanadu, in fact, of applying LLMs to quantum could be really quite exciting. I mean, honestly, I could talk all day with you about this subject. Unfortunately, I'm running out of time. But I'm sure we'll be around, and you'll be around for some questions right at the back, maybe, if anyone wants to ask. But,
sure.
But Christian Weedbrook, CEO and founder of Xanadu, thank you so much for coming to GITEX. And from me, Mike Butcher from TechCrunch, have a great day, everybody.
Thank you.
Thanks. Bye-bye.
Thank you so much. Thank you. Thank you once again, Mike. Thank you. Session expertly moderated there by Mike Butcher, editor-at-large, TechCrunch, and a wonderful insight there with Christian Weedbrook, CEO and founder of Xanadu Quantum Technologies, all the way from Canada. Such a wonderful way for us to continue day 4 here at Expand North Star, our dedicated startup event here in our brand new venue at the Dubai Harbour. I hope you all feel that you're enjoying yourselves and also getting a chance to really get to meet some of our speakers and delve into the intellectual discussions that have been taking place both on stage and off stage.